A very good morning to all of you. Myself, Professor Meandrag from the group of presenters. So, in previous lecture, we have seen the boundary layer concept. So, in this, we have seen the boundary layer theory. Boundary layer theory, it will fill the gap between the Navier-Stokes equation and Euler's equation. So this concept of bounded layer, we have seen that uh, what is the bounded layer? So if in a free stream flow in a canal, if we insert any flat plate or any object, then around the object or around the plate form a boundary layer, and their velocity is different, and that velocity at the extreme velocity is u, then at the uh, at some distance L del the velocity will be uh, prior to uh, same as a free stream velocity. So free stream velocity is u zero. Then here at the when the boundary layer at some distance at L del, this is the distance del, will be nothing but here 99% of u0, and if you write down 0.99 u0. This concept of the boundary layer we have seen in the previous class, and also we have seen the different thickness regarding with the boundary layer theory. Okay, so that is uh, nothing but the del star or delta star is called as displacement thickness. Delta m, delta theta or delta is called as momentum thickness. Delta E is called as energy thickness. Okay, and the ratio of del star and delta m is shape factor, and shape factor is denoted as h. All this we have seen in the previous class. Okay. Also, we have seen in previous class this already thickness we have discussed, and how the displacement of boundary layer is done. The same area here you can see you can see this same area, this area. Okay, due to the retardation of that velocity, it, it pushes back or displaces the same area, the boundary. So boundary layer is here, but it pushes the distance del star due to this retardation, and that's why the displacement of boundary layer will be takes place, and that displacement is denoted by delta star, del star. Okay, so that is nothing but displacement thickness, and due to the momentum, you find out the momentum thickness delta m or delta theta also using the same condition of boundary layer, and then we find out the kinetic energy is nothing half into mass into velocity square. So using the kinetic energy also we find out the kinetic energy, or it is called energy, or it is called energy. Okay, so that's why that we have covered in the previous class uh, up to these thicknesses, and we have solved one example also based on that formula. So for the following velocity distribution in the boundary layer, the velocity distribution u upon u0. U0 is the free extreme velocity, u is the velocity inside of your boundary layer. That is, this is given the velocity distribution half into y upon d, and this example we have seen using this four formula, that is displacement thickness 0 to del 1 minus u upon u0 dy, theta or delta m 0 to del u upon u0, 1 minus u upon u0 dy, momentum thickness, and energy thickness 0 to del, that is u upon u0, 1 minus u square upon u0 square into dy, and the shape factor, that is del star upon delta m or del star upon delta theta, it is called as shape factor. This also we are going to use this. So up to this we have covered. We have just was taken del dn n is equal to y upon del and dn is equal to dy upon theta. Then we put the boundary condition y is equal to 0, n is equal to 0. If y is equal to del, n is equal to 1. Okay. This boundary condition we have put, and then we find out del star 3 by 4 of del, then you find out the theta, that is delta m, that is momentum thickness. It is somewhat coming 2 by 3 of del, and then we have find out delta E, that is energy thickness, which is coming 7 by 32 of del, and then shape factor 9 by 8. This problem we have solved in previous class. Now today we will see the local and mean direct coefficient. Today we will see local and mean coefficient. Page 29. Local and mean drag coefficient. Drag coefficient. So we will see this. Okay. Yes, students, you should go and left turn. So if you see that to find out the local and mean direct coefficient, so we have to find out the first one KARMAN. This is the scientist based on that one KARMAN, or you can write down one KARMAN momentum momentum integral integral equation. Okay, so the same figure you have to draw, guys. The plate having a length L, okay, at a distance of x, okay. This thickness is px, and the length of plate is L. Draw this figure. It is important. Draw this figure. Okay. And again, the free extreme velocity we discussed here. When there the object is not inserted, that is u0. Okay, u0 is the free extreme velocity. So here at the boundary layer, so you can see the velocity distribution inside the boundary layer will be at the distance del. It is here the free extreme velocity is u0. Okay, and at distance, some distance in y direction, at distance y, the small strip we consider having a thickness of dy, having a thickness of dy, having a thickness of dy. Okay. So here, and width of plate, I'm not drawing that width of plate, how many width of plate that is nothing but the width of plate is B. Okay, I'm not here writing the B, and this is the tail distance. Okay, and at this point, you know that it is 99% or 0.99 of zero. Okay, so this is so let us the drag force. Let us let us let dx is equal to drag force at distance x from leading edge of the plate. तो जहां से आपका फ्लूइड फ्लो हो रहा है इस डायरेक्शन में जो प्लेट का लीडिंग एज है जो फ्रंट वाला एज है इसको क्या बोलेंगे हम लोग दिस इज द लीडिंग एज दिस इज द लीडिंग एज इससे पहले भी मैंने बताया कंसेप्ट एक्सप्लेन किया on this back side of that plate the flow is called as trailing edge trailing तो यहाँ पर at distance x from the leading edge तो इसलिए डिस्टेंस यहाँ से बताया कहाँ पर ट्रेलिंग लीडिंग एज से ओके of the plate that is drag force at distance x that is dx okay take out a small strip take small write down on your paper then only you will understand and take a small strip of thickness dy dy at distance y from the plate from the from the plate from the plate okay from the plate. Okay, so this you can see in the figure I have denoted this is the small strip you have taken that thickness dy at a distance y in the y direction. If you say this is the y direction, this is the x direction. Okay, so in y direction, I have taken a small strip inside the boundary layer thickness, a small strip having a thickness of dy in y direction, and and a distance of y from the your flat plate which is inserted into the flow है ना जो फ्लो के अंदर एक फ्री फ्लो हमारा है कैनल के अंदर या रिवर के अंदर जहां भी आप समझिए उसके अंदर हम एक फ्लैट प्लेट इंसर्ट कर रहे हैं है ना उससे क्या होगा बाउंड्री लेयर फॉर्मेशन होगा फ्लैट प्लेट के अराउंड है ना तो थिकनेस जो बाउंड्री लेयर के ऊपर है वो हमारी फ्री स्ट्रीम वेलोसिटी u0 है और बाउंड्री लेयर और फ्री स्ट्रीम वेलोसिटी के बीच में जो बाउंड्री लेयर का सरफेस है जहां पर वो मीट होते हैं वहां पर जो वेलोसिटी होती है वो कितनी होती है वो वेलोसिटी होती है 0.99 u0 है ना या फिर आप उसको बोल सकते हैं 99.99% ऑफ कहां पर जहां पर आपकी बाउंड्री लेयर ट्राई टू match with the velocity of free stream velocity. Okay, free stream velocity. तो हमने पिछले भी देखा कि जब भी कोई ऑब्जेक्ट है हम को इंसर्ट करते हैं तो बाउंड्री लेयर बनती है और वो बाउंड्री लेयर इज वेरी स्मॉल ओके तो ये बाउंड्री लेयर बनती है और एट द डिस्टेंस ऑफ डेल बाउंड्री लेयर फ्री स्ट्रीम वेलोसिटी के से मैच होने की कोशिश करते हैं ये हम लोग ने प्रीवियस क्लास में देखा ओके नाउ small strip of thickness dy at a distance y from the plate, then the mass of fluid, mass of fluid flowing through strip, flowing through strip. This strip is inside the boundary layer, flowing through strip equal to rho small u because inside of boundary layer d into dy, the thickness of boundary layer is dy, the small thickness, that is the mass of, of the stick flowing through that with velocity u, and and change in velocity flow, change in velocity of flow is nothing but u0 minus u, चेंज इन वेलोसिटी है ना. क्या हो रहा है वो u जीरो से क्या हो रही है u में कन्वर्ट हो रही है बाउंड्री लेयर के अंदर जो है दैट इज u0 माइनस. व्हाट इज द ड्रैग फोर्स एट x. तो ड्रैग फोर्स एट x force can write down at x is pulled from the leading edge is dx is equal to 0 to del because our velocity is changing from 0 to del. It is not, it is parabolic. Here it is 0 and at distant del is matching with the u0. That's why 0 to del. Mass, you know, rho u b dy at the small strip because we are finding a distance x for the small strip and u0 minus u is the change in the velocity into this one. Okay. Now about equation, the right on equation. Multiply, multiply, and divide and divide by u0 square. Multiply and divide by u0 square. तो ये क्या हो जाएगा dx is equal to 0 to del rho u b dy u0 minus u into u0 square upon u0 square. So multiply and divide by u0 square. Okay. B is the width of plate. Okay. So if I will take this, what will be the drag force? Rho b u0 square. Because the spin velocity there is not changing. 0 to del. I will take this u0 outside, u upon u0. This u is already there. Yeah. So if I will take it, so what will be? U upon u0, 1 minus u upon u0 into dy. And you know that this u upon u0, 1 minus u upon u0 dy, it is nothing but the momentum thickness delta or delta L. So we have seen already this. So we have previously derived this delta N theta is equal to 0 to del u upon u0 1 minus u upon u0 into dy. So that is theta. So what is the drag coefficient now? So dx at distance x, the drag coefficient will be rho u0 square b into theta or into delta n. Here Here theta is equal to momentum thickness. Theta is equal to momentum thickness. Okay. Now, if I will derivate the drag coefficient d into dx is equal to rho into u0 square theta, then it will be d theta. Okay. So d theta, if you write down, is equal to d theta is equal to, it will be write down 0 to 10 u upon u0 1 minus u upon u0 to dy. Okay. Also this d by dx, that the derivative of that is nothing but tau 0 into d dx. Tau 0 is the shear stress. And here we know that tau 0 is shear stress is nothing but dou u upon dou mu times dou u upon dou y at y is equal to 0. At y is equal to, so I will write down, so will be first dou by dou x is nothing but rho u square, rho u square theta into d into d theta is equal to tau 0 d into dx. If you, by putting this all this term into the above term of the equation, so if I write down this 1, 2, 3, so that will be good. This is 1. So multiply equation 1 and divide by u0 square. So we'll get this by write down the 2 dx. And if you are write d into dx, that is equation number 3. And you know that d theta is equal to u upon u0 1 minus, that is the momentum thickness. It is nothing but the momentum thickness. Okay. And also d by dx is shear stress into that small area, okay, due to the viscosity. And tau 0 is also mu upon dou u by dou y at y is equal to. If I write down for equation 3 and equation 3 and equation 4, so it will be denoted this become equation number 5. Okay. Now this d into d will be cancelled. So what will be? Where I down is tau 0 on rho u square 0 will come here, and d theta will put here as it is, and d dx I will take here. So d theta upon dx is equal to tau 0 upon rho 0 1. This equation number 6. I will write up. So this equation 6 is known as known as one karman, one karman, one karman. Momentum integral equation. Momentum integral equation. So we can draw this equation like this. Let let FD is equal to drag force, drag force on plate, on plate of length x is equal to L. X is equal to x is equal to L. Okay? X is equal to L. Then you can write down FD is equal to, because we are taking is equal to 0 to L d of dx, because we have to find out FD, and that is equal to 0 to L tau 0 d into dx, d into dx. Okay. Now we know that the CD is equal to average coefficient of drag, average coefficient of drag, or you may say that it is mean drag coefficient, mean drag coefficient. So this CD is nothing but it is a ratio of, if you write down, mean drag coefficient CD is a ratio of the actual drag force, the actual drag force upon theoretical drag force, that is FD actual to the FD theoretical. Okay, so whatever you can write down FD theoretical. So it is a ratio of this. So you can put that CD will be equal to FD upon half into rho A U0 square. Or you can write down FD is equal to CD into half rho A U0 square. Where we know that CD is the mean drag coefficient, mean drag coefficient, coefficient, sorry, and U0 is the free stream velocity. U is the free stream velocity. And rho is nothing but the mass density of fluid, mass density of fluid, mass density of fluid. A is nothing but surface area of plate, surface area of plate, and it is nothing but A is nothing but B into L, B into L, B into, okay. So this is nothing but your mean drag coefficient, and if you write down the local coefficient of drag, coefficient of drag. It is denoted by CF or sometime it is series star. It is denoted by that, and that is nothing but it is a ratio of is a ratio of sorry it is a ratio of this shear stress that is shear stress variance tau zero to the quantity quantity of one Karman quantity, you can say quantity that is half rho u is 0 square. You can say it is average velocity into mass density, whatever you use, and it is generated by CF or CD. If you write down CF, the local drag coefficient of CD star is equal to the ratio of shear stress tau zero to the half of the rho into u zero square. So this is the local drag coefficient. This is nothing but CF is nothing but local drag coefficient. CF or CDS. Okay. So there is write down the boundary condition of the velocity profile. Write down. So this is used for preparation of the velocity profile. This is used for preparation of the velocity profile due to boundary layer. Due to boundary layer. Boundary layer का अगर velocity profile हमको बनाना है, the flow velocity, then we can use for this. And for that, what boundary condition will be used? So write down the boundary condition, the boundary condition, boundary condition, condition for for velocity profile, for velocity profile. Okay. So you can write down these boundary conditions. The boundary condition for any boundary condition for any boundary layer condition or any boundary conditions for boundary layer problem, boundary layer problem, or you may write directly for any boundary layer problem, whether it is whether it is laminar boundary laminar boundary layer zone or turbulent boundary layers. Turbulent boundary layer zone. Generally, laminar transition or turbulent boundary layer zones are there in the flow, and we insert some object into the flow layer zone. Then following 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 are the boundary conditions boundary conditions which must be which must be satisfied satisfied by by any velocity profile. Any velocity. So what is the boundary conditions we can take? First, at y is equal to 0, a distance y from the flat plate, it is already, if I will say that this is our figure, so here this distance at y is equal to 0, from here, you can say at this place, so y is equal to 0, then the velocity also 0 inside the boundary layer. Now, you can write down if at y is equal to 0, y is equal to 0, it's y is equal to 0, the velocity inside the boundary layer, that u is equal to 0. Sorry. And dou u upon dou y has has some finite value, that is change in velocity and change in time, that has some ratio of change in velocity present, that is some finite value. Okay. Now second condition, if you write down second condition at y is equal to del, it means that q is equal to u0. So at the distance y is equal to del, from the figure you can understand this figure, sorry, here, at here, this is the boundary layer, you can see the green line. At here, what happened at distance del, at y is equal to del, your velocity will be, you will try to change or convert into u0. So that is the boundary condition you can use for any profile. So you can write on u is equal to u0. And third boundary condition, to make this velocity profile a different section in x direction, because flow is the fluid is flowing in the x direction, and y is considered as depth of your channel. हमने कितनी नीचे आपका जो ऑब्जेक्ट है, फ्लैट प्लेट है, वो इंसर्ट किया है, या एनी ऑब्जेक्ट यू आर इंसर्टेड एट y is equal to del the slope du upon dy must be is equal to 0, because the velocity at y is equal to del is nothing but nearby equal to the free stream velocity. So you know that u0 is nothing but your free stream velocity, free stream, okay, and u is nothing but velocity of flow inside the boundary layer, inside the boundary layer. Inside the, okay, so we will you can understand this. What is the drag coefficient? Drag force uh, at a distance of L, from the figure you can understand, to make a velocity profile for the one Karman momentum integral equation may be used, and there are two drag coefficient you can study, and that is local and mean drag coefficient. And we have written that local drag coefficient is the ratio of shear stress to the quantity half into rho into u square, and drag coefficient CD is a ratio of actual drag force to the theoretical drag force. Okay, so this is you have to learn using this KARMAN velocity integral, one KARMAN equation for momentum integral equation. Sorry, one KARMAN momentum integration. From that we can derive the average coefficient of drag or mean drag coefficient CD, that is local drag coefficient EF or CD star. Okay, so for the this is the today's lecture based on the local and mean drag coefficient. We'll start the बाउंड्री लेयर सेपरेशन. अभी बाउंड्री लेयर फॉर्मेशन हम लोगों ने देखा और उससे रिलेटेड टर्म्स. अब कुछ डिस्टेंस पे जाकर आपकी बाउंड्री लेयर क्या हो जाती है, सेपरेट हो जाती है अगर कर्व सरफेस है तो. ओके, otherwise it will be the wave formation, and that will be in the next class. Next class I will start from 11:10 a.m. So now only 5 minutes are left, and my mind it will not cover. So we will stop here, and we will continue your last topic of unit number 3. Okay. Thank you for joining, and we will continue our